Assalamu alaikum wa rahmatullahi wa barakatuh. The purpose of these videos is, inshallah, will help you catch up on some of the material you missed out on in case you were absent or if you want to revise for the quizzes or if you didn't understand the topic properly in class. Inshallah, you can always refer back to these videos. Okay, so we're going to do Unit 4.4, which is projectile motion. Um, that's what's happening here. Okay, so what I'm going to do is I'm going to read through these and explain them the way I would do in class. And so hopefully it'll help you prepare as well, because what I plan to do is inshallah with the next few sets of videos, what I plan to do is inshallah I will post them in advance. And so we can have a reverse classroom going on. So what that means, the reverse classroom is you actually watch the video before coming to the lesson. So I will post it in advance, you watch it, you come to the lesson, and then after I finish my sharh, after I finish my explanation, inshallah you'll feel better about the topic and you'll understand it properly. The whole point of this is to help you out, so please make the most of it. In Zain, we're talking about projectile motion. So what is projectile motion? In short, projectile motion describes any object that is launched, that is kicked, that is thrown, that is free falling. Yes, free falling is part of projectile motion. Any object that has no external forces acting on it beyond gravity. So only gravity is acting on it. So once you throw this pen, for example, if I throw it, what's going to happen to it? It's going to continue moving. But there is no jet engine on it. There's nothing that's going to affect it in any way. It's just going to be controlled by gravity. That's it. طيب. There's very important points to talk about on this page, which is let's have a look. So it is determined solely by gravity, so the influence of gravity. But there are some assumptions to be made. So air resistance can be ignored. We are ignoring air resistance completely for projectile motion. So we're dealing with ideal conditions here. But I do want you to understand that obviously air resistance does affect objects that are moving through the air, but we are ignoring it completely for this case because it is negligible. The other thing I want you to know is that gravity is going to be 9.81 meters per second squared. In short, projectile motion describes the motion of an object using two different dimensions or with two different axes. So we've got the x and the y, and the x is the horizontal motion, while the y describes the vertical motion of the object, and that is basically the condition for projectiles. Okay, so let's have a look at what this means. Okay, so because horizontal and vertical motions are independent of each other, so they are actually independent. So what does that mean, independent? يعني مفصولين عن بعض. يعني the horizontal motion ما له علاقة, does not have to do with the vertical motion. How is that? شلون? Well, I'm going to give you an example to think about. Think about outer space. Think if you are in outer space and you throw an object, right? That object is going to continue moving because there is nothing influencing it. How is it going to continue moving? Like in what form is it going to continue moving? It's going to be moving at constant speed. Whatever the speed was at which it left your hand, okay, it's going to continue moving at that speed through space. And nothing is going to stop it. Assuming there's no gravity, assuming there's no external forces, it's going to continue moving at constant speed. Now, I want you to imagine that same scenario, except now there is a source of gravity. So let's imagine we're on the moon. The moon doesn't have an atmosphere, there's no air in the moon. So basically, you throw an object, it's going to continue moving, but then suddenly gravity is pulling it down. Now, it so happens that those two different motions, so there's the horizontal motion where it keeps going this way, and then there's the vertical motion, which is downwards, are completely independent. They don't rely on each other. They have no connection with each other. Okay? So we can actually work out each motion and determine certain things about the object and its flight path and so on. But that's where we're getting to today. So far what we've covered is the following. We've got two different motions. We've got the x-axis, the motion in the horizontal direction, and we've got the motion in the vertical direction. All right? So we've got this motion here in the horizontal direction, and we've got this motion here acting downwards. Why? Because gravity is pulling down on it. So if we throw this object, it's going to go this way, and then finally it's going to end up over here. So the flight path of the object is going to be a combination of those two motions. But turns out the only thing that determines the time of the object in flight is actually just the y. And we're going to come to find out why that is now. So let's have a look. These are the position-time equations for projectiles. Position-time equation. Now remember, we talked about these when we were talking about kinematics. Okay? When we were talking about motion in 2D and constant acceleration and all of that. So the 5 equations that we talked about. Now, this is exactly the same as what we've been studying. Do you remember this equation? Change in x equals v VIT, which is the V initial, velocity initial, or initial velocity, multiplied by time, plus half AT squared. Now, some of you, if not all of you, will be familiar with this equation. Okay, this is the equation that we used for the end of term 2 exams as well. So we use this equation quite a bit. This is going to help us. So if we want to find out the x position, if we want to find out the position of the object in the x-axis, then all we need to do is apply this equation. And if we want to find in the y-axis, it's the same equation. But turns out we can rearrange this equation, because what is delta x? That just means change in the x-axis. So we've got x final, which is the final position, minus the initial position, Yisawi, okay, VXIT. Now that's just fancy word for velocity in the x-axis initial. So the initial velocity in the x-axis multiplied by t plus half AT squared. Now plus half AT squared. What is A? What is the value of A when we are in the horizontal direction? Remember what I said. Once you throw an object, you no longer have control over it. There are no external forces on it. The velocity of the object is going to stay constant. It's going to continue moving at whatever speed it left your hand. Therefore, it has no acceleration. No acceleration means A is going to be 0. If A is 0, this whole thing is 0. It doesn't exist. So therefore, we have this equation. Now we can rearrange it. XF Yisawi VXIT plus XI, or the other way around, which is what they've done over here. There is no acceleration in the horizontal axis. Okay? There is no acceleration in the horizontal axis. So what that means is if an object, a projectile, once it's launched, if you're hitting a ball, or if you're throwing a basketball, or if you're shooting a bullet, once it leaves the chamber, okay, assuming there's no external forces acting on it, it's going to continue moving at the same speed. Okay, that's under ideal conditions, obviously, where we ignore air resistance. Okay, so that's what that's going to be for x. Let's have a look at y. So y is a different case. Why is it a different case? Okay, why is y a different case? Let's have a look. So the story with y is the same as the story for x, except we have acceleration in the y-axis. Where is this acceleration coming from? So some of you would have figured out that it's coming from gravity. Gravity is pulling down on the object, which is why if it was in space, it would continue moving in its path. But because here on Earth or any planet or the moon, there's gravity pulling down, so therefore the object is going to slowly start going down, right? And once again, the equation is plus half at squared, but since the value of a is negative 9.81, why negative? Because it's pointing downwards, so we can just write it as negative half gt squared. It's exactly the same formula. So you can see here, once again, x in the x and the horizontal direction, there is no acceleration whatsoever, constant, while in the y direction, there is acceleration towards gravity, and that's why we have that. Okay, let's go to the next slide. We're nearly done with the explanation. We're going to start doing some questions soon, but here we have a good example. So we have this guy here who's on his skateboard, and he lets go of the ball as he's skateboarding. Okay, so he just releases the ball. He's not throwing it, or he's not throwing it. He's just letting go of it. But since he's moving at 1.3 meters per second, he's moving on the skateboard at 1.3 meters per second, which means the ball is moving at 1.3 meters per second. So he releases it, and what does it do? It bounces in front of him. So therefore, the ball has a speed or has velocity in the horizontal axis. And well, it starts off at 0 because he's releasing it in the y-axis, right? In the x-axis, or in the horizontal axis, it's moving at 1.3 meters per second, but because he's releasing it, just much like this pen, he's releasing it, which means it starts at 0 meters per second in the vertical axis. So the initial velocity in the x-axis is going to be Vxi is going to be 1.3 meters per second, and Vyi, which means the velocity in the y-axis, initial velocity in the y-axis is going to be 0 meters per second. Once again, why is it 0? Because the guy is releasing the ball. He's not pushing the ball down. He's not doing any of that. He's just releasing the ball as he's moving. Right. Now that we've got those two terms, what is the question here? Well, there isn't much of a question. It's just telling us what the formula is going to look like. Okay, why does the formula look like that? Let's have a look. Well, the formulas that we're going to use are over here. These are the position time equations for projectiles. Let's have a look. The initial position in the x-axis is 0. The initial position in the x-axis is over here. That's the y. That's the x. Okay? And as you can see, the ball starts over here, which is x0. But y is not 0. Y is at 1.25, as you can see here. Y is at 1.25. So since the xi, the initial position of x, is 0, then that equation becomes, well, let's write it out first, xit. It becomes 0 plus, and what is the initial velocity for the ball? Well, it turns out it's the same as the guy, multiplied by t, and that is going to give us the final position. We can simplify that further by saying xf equals 1.3 t, which is what they have over here minus the units. Okay, that makes sense. That makes sense. Okay, let's look at the y-axis. Let's look at the vertical motion this time. So what do we have here? We have, once again, we have another formula. And, sorry, it just takes a little while to use my stylus to rub all of that off. So here we have a different formula for the horizontal, for the vertical axis now, for the vertical motion. So what is that going to look like? We've got YF Isawi, the initial position, I'm going to write it out first. I like writing it out again. Just makes it easier in my head. And I think it's good practice, because then what you can do is do something like this. I'm going to use orange. I'm going to be very brave. I'm going to say y, the initial position in the y direction. Let's have a look. What is that? Well, we can look over here and we can see that it's 1.25 meters. So the ball was dropped from a height of 1.25. So that's going to be the initial position. What is the velocity in the y direction. What is the initial velocity? Well, remember it was dropped. It was dropped. So that means the initial velocity was 0. Why 0? It was dropped, and then it started accelerating down. So since it's 0, that's going to be 0 times t, which means it's 0. So plus 0. And sorry, minus half gt squared. Well, we know what g is. G is 9.81. So minus half times 9.81 t squared. And we can simplify that further. Let me use a different, let me use a different color because that is a little bit hard to see. 1.25, sorry, y final, which is the final position in the y-axis, is going to be 1.25 minus half times 9.8 t squared, which is what we have over here. Remember, g is constant, or we assume it is. Okay, so hopefully that's clear. Let's go to the next slide. Right, so now we have some questions to do. We have this example. So the person skateboarding with a constant speed of 1.3 meters per second, remember that's the horizontal speed, the horizontal motion, releases a ball from a height of 1.25, releases the ball. Now remember, these words are important. He releases the ball. He doesn't push the ball down. He doesn't forcefully bounce the ball. No, he releases it, simply releases it, which means it is falling down with the effect of gravity. It's free falling. Okay, so this is a classic example of projectile motion. And so we have the starting position, we have the starting velocity, and what do they want? They say, given that xi, which is the initial position in the x-axis, is 0, and yi, the initial position in the y-axis, is 1.25, find the final position in the x-axis and the final position in the y-axis, right? So they want us to find the positions in each of the independent trajectories, and then with at two different times, at 0.25 and 0.5. Okay, let's have a look. So how do we do this? Well, it's quite simple. We've got the formulas. Do we have everything we need? Let's have a look. So we want to find xf at 0.250 seconds. Let's have a look. xf is going to be the initial position of xi is 0 because it starts off as 0, and then vxit. So the speed in the horizontal axis is going to be 1.30, which is the same as the speed of the person, multiplied by 0.250. And that is going to give me 0.325. It's always a good idea to try and pause the video and do it yourself, and then check your answer. Okay, what is the unit here? Well, we're talking about position and we're working with meters, so it's going to be in meters. What's going to be the final position in the y-axis? Well, that's going to be, let's have a look. The initial position is 1.25 meters plus the initial velocity. Remember, we said that was going to be 0 because it got released. So the y velocity, the initial velocity in the y-axis, is going to be 0. So that is 0 plus or half gt squared, or you can just say minus half times 9.81 times t squared. Okay, so we know we can simplify that further by saying 1.25 minus half times 9.81 times 0.250 squared. That's the time. That's g, acceleration towards gravity. And that is going to give us a number which is 0.943 meters. Now, before we continue, okay, I want you to start getting to the habit of, does this make sense? Well, let's have a look. After 0.25 seconds, after ربع ثانية, okay, after ربع ثانية, is it possible that the position in the x direction is going to be about 32 centimeters. Well, let's see. If he releases it as he's moving, and he's moving, and he releases the ball, is it possible that it's moved about 30 centimeters that way? It kind of is. So I want you to think about it logically. And then, is it possible that the position has gone from 1.25 meters down to 94 centimeters? So from 125 centimeters down to 94 centimeters in Ruba Thania, that's also possible. Yeah, so that makes sense. You know, physics is just about making sense, right? If you understand it, you don't have to learn anything. You don't find it difficult if you understand it. That's counterintuitive. Of course you don't, but you know what I mean. Right, let's have a look. So what else do we need to do? We've just answered A. What do we do for B? Well, same exact thing. We just change the numbers. So you can go ahead and do that if you want to. I am going to do it as well. So I'm just going to change those numbers here. I'm going to put that. I'm going to take out those answers because obviously now the numbers are different. So I'm going to substitute 500 here and substitute 500 here, 0.5, and that should give me 0.650, and that once again makes sense because obviously the ball is moving forward, so that number is more. Okay, so after half a second, the ball is actually moved further forward. So here it is at 0.25, here it is at 0.5. That makes sense. And what's going to happen to it in the y-axis? It's going to be less because see, it's going down. It's close to the floor. So what's that going to be? It's going to be 0.024. 0.024. Okay? So that means it is, in fact, 2 centimeters away from the floor. Very, very close to the floor. Makes sense. Okay, so that means it's nearly hitting the floor. That's all that means. And that's how you do that one. Let's go to the next example. It's a follow-up. How much time does it take for the ball to land? How much time does it take for the ball to land? Well, it turns out how much time it takes for the ball to land is easy to calculate because remember what we said. We said that the time depends on the y and not the x. Okay? So what do we have? We've got the distance, which is, what is the distance? 1.25. So really what we're trying to find out is how long does it take that ball to travel 1.25 meters. So we have the initial position and the final position, so let's do that. So we've got the final position as 0. So that, let's just write it again. Remember, I like to do that. I always like to write it again. Minus half gt squared. Okay, I feel like writing in green. Let's have a look. So the initial position is going to be 0. The final position. So the final position is 0. The initial position is 1.25. The initial velocity is 0. Why? Because it was released. And then minus half times 9.81 times t squared. Okay, so what you can do is you can use your calculator and solve for x, replacing t with x, but I like to do it the old-fashioned way. So what I'm going to do is I'm going to do swapsies, so I'm going to put that on the left-hand side, and because I'm putting it on the left-hand side, I'm going to minus 1.25 from the right-hand side, I'm going to minus 1.25 from the left-hand side. So I'm going to do it in steps here so everybody understands it. Multiplied by 9.81 multiplied by t squared. Oh, that's a terrible t. Let me fix that. Multiplied by t squared. Now what am I trying to find? I'm trying to find the time, so I'm trying to find t. Okay, so what I can do is I can take this to the opposite side. How do I do that? Well, this is multiplication, so I have to divide. So if I divide by negative half times the 9.81 on the right hand side, I have to divide by negative half times 9.81 on the right hand side times 9.81, and طبعا those two cancel, and I'm left with t squared equals that. Well, I can do one better, but I don't want t squared, I want t. So all I have to do is square root that. And that will give me t يساوي, let's have a look, 1.25 divided by 0.5 times 9.81. And that is 0.25, square root of that. Now, before I get the answer, I expect the answer to be very close to 0.5. ليش؟ لأن remember at 0.5, which is what we worked out here, y was very close to the floor. It was 2 centimeters away from the floor. يعني تخيل الكرة هذا الفلور, and the ball was just about to hit the floor. Just about to hit the floor. So how long is it going to take to hit the floor? Maybe less than a tenth of a second, a hundredth of a second. So 0.5, very, very close to 0.5. That should be the answer. Now let's work out the answer. The answer is equals, equals 0.505 seconds. Makes sense. Very close to 0.5. Yeah, it was almost hitting the floor, and then it hit the floor. So that's how you solve that one. That is number 36. Okay? Let's look at number 37. Oh, I have a lot to rub out, and I hate to do this. Where is Duerji to help me out? Okay. Right. So the next question is talking about archers, which is a person who's shooting an arrow. An archer shoots an arrow horizontally at a target that is 15 meters away. Okay, so let's draw the arrow. And he is shooting the arrow at a target that is 15 meters away. Okay? Does that matter? Not really. But anyway, the arrow is aimed directly at the center of the target, but it hits 52 centimeters lower. Now that matters. So the person aimed it at the middle of the target, the bullseye, but it ended up hitting 52 centimeters below. We're going to write that in meters, 0.25 meters below. So it went like, and it hit here. Okay, what is it asking for? How long did it take the arrow to reach the target? Do we care about the x-axis? No. Remember I told you a bullet shot and a bullet dropped will hit the floor at the same time. I know it's counterintuitive, but that's what happens. In fact, you know what? Before I continue solving this, I'm gonna show you this video that I really like, and it's this one here. Okay, check it out. So this is a demonstration. Oops. Oh, sorry, I'm having some technical difficulties. Here we go. So this demonstration shows, before we continue, the difference between an object that is dropped and an object that is shot. All right. Now remember what we said. The y motion, the vertical motion, is going to be the same for both. Even if one is shot, or even if one is pushed, they're going to reach the floor or they're going to reach the ground at the same time. Okay? And this here shows that. So watch this. So that one's going to drop straight down while this one's going to be shot. I want you to watch and see how they both reach the ground at the same time. Okay? Very interesting. Let's watch that again. Excellent. Which is what we expect to see. So knowing that, we know that the distance in the horizontal axis doesn't actually matter. Okay, so even though that ball traveled further, didn't really matter. They reached the ground at the same time. So this is what matters here: the y axis, the distance in the y axis. Right, so in that case, we don't actually need to worry about that. So we just need to look at that. So let's have a look. What is the final distance? The final distance is 0.52. The initial was 0. What is the initial velocity in the y-axis? The initial velocity in the y-axis was 0. 0. How? Well, when they shot the arrow, it was speeding in the x-axis, but they didn't mean for it to go down. They hit the bullseye in the middle, but started going down. Why did it start going down? Because of gravity. Because of gravity. So that means it was falling due to gravity. So the initial velocity in the y-axis is 0. The initial velocity in the x-axis, oh, it's traveling very fast. Okay? In the x-axis, whatever the velocity was, it was traveling very fast. Um, Depends on what the time is, but I would say it's probably about maybe 30, 40 meters per second. However, in the y-axis, it was 0 because it very much just dropped due to gravity. Because it's 0, this whole thing here becomes 0. So 0 plus 0 minus half times 9.81 times t squared. So alhamdulillah, this makes it easy somewhat. So and well, the final position, we can actually write it as negative 0.52 because it's gone down by 0.52. But if you don't write it as a negative, just ignore the negative um, when you're doing the calculations. Okay, so we don't need to worry about that. We don't need to worry about that. Let's get rid of this. So we divide by negative half times 9.81. I just like to show all the steps. And so we do the same to the other side, negative half times 9.81, remember? And then the square root of all of this will give us t. And so t will equal to 0.52 divided by this, and it equals 0.33 seconds. Okay, 0.33 seconds. So it traveled 15 meters in 0.33 seconds. That was traveling, that arrow was traveling pretty fast. It was traveling at a rate of 45 meters per second. Yep. Okay, so that's how you work that one out. Let's have a look. All right. Projectiles follow parabolic paths. Well, I think we know that already. You've seen that drop basketball in figure 4.25 follows a curved path. Let's have a look. Yes, it does. Over here. See, it follows a curved path. Curved path. Okay. And so, let's examine this motion more carefully. Look at figure 4.26. So this is this figure here. All right. What's going on in this figure? Well, there are two very interesting things happening here. What you'll notice is that in the horizontal direction, in the x-axis, shows the x position and the y position of the basketball a variety of times during its fall to the ground. Okay, notice that the horizontal position of the ball increases steadily with time. The horizontal position increases steadily with time. Why is that? Due to acceleration. There is a change in velocity, therefore it increases. So look at this, and then look at that. Look at this gap, and compare that to this, and compare that to this, and once again, and you can see the gap increases. Okay, whereas that's in the y-axis, whereas in the x-axis it stays consistent. Why? Because it is constant velocity. There's no change. There's no acceleration, and that's what it's telling you over here. So Notice that the horizontal position of the ball increases steadily with time as the expected for constant speed. It's constant speed. The vertical position, however, changes by increasing amount with each time because of gravity, 9.81. So it keeps increasing, increasing, increasing. So what that means is every second it's increasing by 9.81 meters. Okay? The velocity, that's. Or the speed downwards. In general, ideal projectiles follow a parabolic path regardless of how it's launched. Yes, yes. The only exception that I can think of is free fall, and that's because there's no x direction whatsoever, right? Okay, and the other thing now we got to talk about is velocity time equations. So we've talked about position time equations. We're going to talk about velocity time equations. Now, if you remember, this guy over here, okay, so we should be familiar with this guy over here. The final velocity equals the initial velocity plus acceleration times time. Final velocity equals velocity initial plus acceleration times time, all right? So once again, since we're working this guy out, that's what we were looking at. It's made of an x component and a y component. Okay, so the x component is going to be the same formula but all in x's, and the y component is going to be the same formula but all in y's. Okay, so that's what that looks like, and that's what that looks like. Okay, except we know that in the x component, there is no acceleration. There is no acceleration, so we can get rid of that completely. We don't need that guy. And since acceleration is negative because it's due to gravity, we can just write minus gt as opposed to plus at, because a is equal to minus g, or minus 9.81. So that's just a fancy way of writing it. So now we have final velocity in the x-axis equals to initial velocity in the x-axis. Does that make sense? Yes, it makes perfect sense. We said there is no change in velocity. Imagine outer space. If you throw an object, it keeps going. Whatever, at the same velocity, constant. So that makes sense in the x-axis. But that's not what happens in real life. Why? Because we have gravity. So therefore, the object will fall towards gravity. If we didn't have gravity, it will continue moving. Right, let's have a look at the y. Velocity in the y equals the final velocity is equal to the initial velocity, which sometimes it's just dropped, sometimes it's launched, sometimes it's shot upwards. Um, but a lot of the time it's zero. And then minus gt, minus g, which is the acceleration towards gravity, times time. So now we have two sets of equations. We have one for position and one for velocity. And they both are from kinematics. Okay, so here's the two sets of formulas together. There's that, and there's that. And we have an example. You throw a baseball from the roof of a house to a friend on the ground. Okay? You throw a baseball from the roof of a house to a friend on the ground. Um, the ball has an initial velocity of 12 meters per second in the horizontal direction. In the horizontal direction. So that means in this way, in this component, it is traveling at, so Vix or Vxi equals 12 meters per second. After 1 second, how fast is the ball moving in the x direction and the y direction? Well, we've got the formula. So it turns out Vxf equals Vxi. So the first one is a bit of a trick question, really. So basically, in the x direction, it's going to be the same as the the final velocity is going to be the same as the initial velocity. It's going to be the same. So if it's 12, then that's going to be 12. If it's 15, then that's going to be 15. It's not going to change. Remember, ignore gravity, ignore the y. It's not going to change. So the first one, A, that's 12 meters per second. Now B, on the other hand, is something else. What's going to happen after 1 second in the B direction? Sorry, in the y direction. Well, we have this formula over here. So velocity in the y-axis, the final velocity, is going to be equal to the initial velocity in the y-axis minus g times t. What is the initial velocity? What did they say? You throw a baseball from the roof of a house to a friend on the ground. Okay, so it seems like the initial velocity was 0. I think that's what they implied. And we get to work out the final velocity, which is after 1 second. So we're going to go with 0 minus 9.81 multiplied by 1. So it seems to be that after 1 second, the speed is going to be, the final velocity is going to be minus 9.81 meters per second. And that's how you solve this example over here. Okay? So I'm going to rub that out and start doing the problems as well. Please do try and do them yourself. Pause the video if you have to, and do them and then follow up with me. Okay, so let's have a look. Follow up, number 38. What is the speed of the ball at time t equals 1 second? What is the speed of the ball at time t equals 1 second? Hint, speed is the magnitude of the velocity. V equals Vx squared plus Vy squared. So now what they want is they want the speed of the ball as it's falling. So what that means is, do I have a ball anywhere? I usually have a lot of things around. We're going to imagine that's a ball. So they want the speed of the ball as it's falling, which means not the x component, not the y component. They want the combination of both. And when an object falls, its velocity is a combination of both components. So there's the pull, but there's also the horizontal launch speed. So it's just basic vectors. So we have the speed over in this direction. Oh, maybe we'll use this direction. 12 meters per second. We worked it out over here. And then we've got the speed in this direction, which was negative 9.81 meters per second. Can we work out the speed in this direction over here? Of course we can, Pythagoras. So it's going to be 144 square root of 144. Why is it 144? 12 squared. 12 squared plus 9.81 squared, which is nearly 100, so 96 or something. 9.81 squared, 96. And that's going to give us V, overall V. Because V is going to be Vx squared and Vy squared. Plus 144, square root of that, and that is 15.5. Does that make sense? Yes. It's going to be more than one or the other, and that makes sense. The hypotenuse is bigger than both. Question 39 says, what is the direction of the motion of the ball? Well, we should be able to work this out as well. This is the opposite, and this is the adjacent. And I'm going to take this out. So the direction is going to be theta shift tan is equal to shift tan, or the inverse tan, of 9.81 all over 12, and that's going to give me theta, which is going to be 39 degrees. Yep. Okay, so that's going to be theta, which is 39 degrees. Okay, below the x-axis. Here we have another example to do, or it's a conceptual problem. So that just means we have to think about it. Two youngsters dive off an overhang into a lake. So it's just a cliff. Diver 1 drops straight down. Diver 2 runs off the cliff with an initial horizontal speed v. Okay, but they both start at vertical speed of 0. They both drop, even though one of them runs and the other one drops straight down. There is nothing pushing them. They both start with an initial velocity in the y-axis, in the vertical axis. Their initial velocity is going to be 0. Just something to think about. Is the splashdown speed of diver 2 greater than, less than, or equal to the splashdown of diver 1? It's very tempting to say that they're both going to have the same splashdown. طبعا, we assume a lot of things when reading this question. The first thing we assume is they both have the same mass. Otherwise, if they didn't have the same mass, it would be different. Because kinetic energy equals half mv squared. So if one of them was heavier than the other, then they're going to naturally have a big splash, unless the other person has a much higher velocity. But assuming they both have the same mass, which is what the question is implying. One of them is running, the other one drops straight down. Which one's going to have a bigger splash? Which one's going to have more energy? Which one's going to have more? More energy means more velocity. In this case, more velocity will cause a bigger splash. In order to figure that out, I want you to think about the previous slide. What was the overall velocity here? The overall velocity here was 15.5. Why? Because it was higher than both, because the hypotenuse is going to be bigger than both of them. So the x component makes a difference. It would have been 9.81 if it was just the y component, but because there was an x component, the splash or the velocity is bigger. Look at this example here. We've got one person with a y component, the other person with the same y component, except this person also has an x component. That means this person's velocity overall is this here, while this person's velocity overall is this here, but it's the same as this. So this one's going to be bigger. This one's going to be bigger. It's going to have a higher velocity. Because it has a higher velocity and it has the same mass, it's going to have a bigger splash. So second person is going to have a bigger splash. The other way you can do these questions is by just simply putting in some numbers. Put in some numbers, why not? Let's say Vy equals 5 meters per second for both. Except this guy has a Vx as well. So let's give him a Vx, whatever. How fast was he going, jumping off the cliff? Just give any number, it doesn't matter. 3 meters per second. What does that mean? That means this guy overall V is going to be 3 squared, which is 9, plus 5 squared, which is 25. Okay. And that's overall, that's 34. Square root of 34 is nearly 6, about 5.8 meters per second. Whereas this guy's overall velocity is just Vy. There is no x component. So this one has a bigger splash. I hope that makes sense. Okay, I'm going to stop there. We'll just call that part one and of 4.4, and inshallah I will be uploading part two soon. Because part two starts talking about launching stuff, which is just as easy, except we just have to use Sokatawa. Okay, thank you. Hope you enjoyed that. Take care. See you next time.